And with that, it's a pleasure to introduce our next speaker who will be talking about AI systems engineering, challenges of a new professional discipline. It's Dr. Julius Pfrommer. He heads a department at Fraunhofer IOSB solving hard AI problems in both industry and academia, and he's furthermore the scientific director of the Competence Center for AI systems engineering. It's a pleasure to have you on board for the next 20 minutes, and the stage is yours.
Introduction, great to be here. We are talking about KI engineering, which we translate as AI systems engineering. So in this talk, I assume that you are all somewhat familiar with artificial intelligence, because I don't have time to start from the very beginning. Today, we will focus on what happens when we apply AI in the context of large, real-world industrial systems. And then it's not enough to just pull out MATLAB, Jupyter Notebooks, whatever tools we have at hand. Then we get into real engineering, and then it gets somewhat complicated. And still we have challenges and also research questions for AI itself, but we have to go beyond. First of all, to set the frame for this talk, let me tell you about an industrial use case so that we are all on the same page, what we think about when we say industrial system. This is a production plant for wood panels. So if you look around yourself, many things are made from wood panels, for example, this desk, or if you buy some kitchen at IKEA. And this is also great for the environment because you can use the entire tree. You don't have to cut small boards out of an entire tree. And these plants, they are 300 meters long, cost upwards of 100 million euro. And they need to be configured and operated and fine-tuned all day, every day. So there are people who know how to react, for example, what happens if the wood changes, or what happens if we have more recycling wood, or what happens if the wood is much more wet today, etc. So there's this very expensive and very energy expensive process, and it has to be consistently fine-tuned. And what we have done here together with Diefenbacher is develop predictive models for the quality, and then we can use that to really drive the system at the limits where we use the least amount of resources in terms of wood and energy. And this then goes in savings in the millions of euro. So it's worthwhile to invest into AI and also to have AI teams over a prolonged period of time that develop this. And I have to say that within weeks we had the first prototype running, but then it took years to get this into production and to get it delivered for the first customer who is then actually running this plant. So most AI initiatives that we see in industry, and there are a lot of them, most of them reach a very successful prototype and then die. And the question is, why is this the case? Why do we see so little, or why is the percentage of prototypes that makes it into long-term productive use so small? And well, this is obviously because it's very difficult. So development of a long-term deployment is a different beast than just banging together a prototype with a small team of 2 or 3 people. And then also it's very difficult to operate the system. Even once it has been deployed, things come up, the world changes, the systems change, there needs to be a real maintenance. So AI systems have to be maintained, similar to a mechanical system where there can be, for example, a degradation over time. And we say that in order to leverage the value that only comes from the long-term use of such AI systems, we need to combine the basic AI research with systems engineering. And we dubbed this KI engineering. So this is like an Anglo-German mixture, because we want to combine also like the strengths of the German industry, who is very strong in classical engineering, together with now AI. And the definition is AI systems engineering addresses the systematical development and the operation of AI-based solutions as part of systems that master complex tasks. Meaning here in this context, we are not only focusing about the AI itself, but it has a particular function within a larger system and also has to be defined and specified in that terms. So the agenda of this talk are 4 challenges of AI systems engineering that we have identified in a long-running project this Competence Center for KI engineering. First of all, I will be talking about application dimensions. So how can we classify the different applications and also then derive impact factors? How does this change the type of AI that we use and also the development approaches that we take? Then I will talk about challenges during development, challenges during the operation of such systems once they have been deployed. And in the end, I will finish with research questions. So what are the long-term developments that we cannot solve in an ad hoc fashion just for a single project? First of all, what is different from normal AI in the types of applications that we are addressing here? And for that, we have identified 3 dimensions that make up this cube. And I will go through them one by one. First of them is the criticality dimension. And here we have the link to the previous speaker. This is about safety, about the safety of human life. And well, in some cases, criticality can also mean business critical functions, data protections, and other risks. So we always have to balance what is the probability of a certain risky event happening and then the impact, and specify our systems accordingly. And I have to say, if we go into the examples of really high criticality, like the operation of an electrical plant, then I have not yet seen true AI in such an environment deployed. So if we go to TÜV Süd, for example, and say we would like to certify according to ISO 61850 or analogously, then today I don't know an example where this was successfully done. And later in the talk, I will talk about some of these reasons. If we go to the mid-criticality level, then it's okay. Then in most cases, it's enough to just show empirically that the system works. The second dimension is the organizational complexity dimension. So if we develop large systems like the one I just showed you, typically there are many different organizations involved. So this can be departments within a big enterprise, but this can also be like a collaboration with AI teams coming from the outside. And this can be also, for example, a difference between the owner of the AI system and the operator. Or with the Diefenbacher example, Diefenbacher builds these large wood processing plants, but they don't operate them. Yeah? So then there's a question, who owns the data, etc., etc. And the third dimension is the physicality dimension. So how much can we derive from prior knowledge about the physical world? How many classical engineering models do we have that we can then integrate with data-driven methods and reduce the number of data required? And to give you some examples as well for the criticality dimension, think about an AI-based automatic airspace control. So most of you flew here probably, and the airspace control is still done by humans. And there were approaches to replace them or to help them with AI-based systems, and this completely failed. So today this is still a 100% human-done task, this airspace control. And the second example for the organizational complexity is patient data in healthcare. And there you can imagine how difficult it will be to collect and evaluate the data. Technically, we can do that, but to do that from an organizational perspective is a wholly different beast. And for the physicality dimension, we are also involved in large projects for the control of electrical grids. And there we have a lot of prior engineering information about the system that we're talking about. Okay. So after these general classification dimensions for applications and what challenges come from them, let's talk about general challenges during development. A very general challenge is the performance prediction. So we would like to get bounds for the performance, and we would like to get that very early on in the development process. So typically, when you get to large system development, we get away from the Scrum or the Agile development models that computer scientists like so much, and we get more into waterfall-like development approaches. And there, at some point, you make a system design, and then you finalize the system design, and then you implement it. And there, you would ideally like to already have performance bounds that you know and that have been validated before you finalize your system design, because afterwards changes become very, very costly. But in AI, well, oftentimes we need to make the system in order to find out how well it performs. The second term is data availability. So we want to have as much data as possible, and we want to have data that resembles the data that comes from operations, and we want to have that before we build the system. And obviously, when we don't yet have the system, this is problematic, and then we have to work with surrogates, or we have to work with simulations, or to somehow manually prepare the data that we need, which is often then much more costly. Third point are heterogeneous deployments. So what you see here on the slide, this is an example with NC milling machines, and you have hundreds of them in a hall, and they've been all bought together, but I can assure you there are differences between them. And if you deploy ML models, they have to somehow figure out what are the differences from one machine to the other and correct for that. Yeah, so you cannot assume that you train your model once and deploy it 100 times. You have to cater for individual differences. And the fourth point is domain knowledge integration. So we have a lot of prior knowledge about our systems, but then we play dump. Yeah? So we throw away all our prior knowledge, take an artificial neural network and let it train from data. And for that, we also then need a lot of data. We could improve the situation by really using our prior domain knowledge, but we don't really know how to infuse that into our neural models. So there are a couple of ways around that, but it's still highly non-trivial. In the development, we not only have technical challenges that are very general, we also have organizational challenges. I already talked about the difference between linear versus iterative or agile development models. And here then we also have different cultures coming together. So mechanical engineers that work very differently from software engineers, and they have to be integrated then into an overall development approach, and also have to understand why one domain, for example, prefers agile development or also prefers to try out different solution approaches before settling on one final. We have the problem of scaling to large heterogeneous teams. So typically in an AML model or in an AI system, there is one system architect who has the entire system in his head and who knows it inside out. And when there's a problem, people can come to him and he understands all the relations of the different parts. But what happens if the system becomes so large that no one person can keep it entirely in his head? Then you have to really strongly talk about interfaces and guarantees made at these interfaces, etc. And then you have, in addition to that, heterogeneous teams from different domains who maybe initially don't even have a language to talk about these boundaries at the interfaces. And then lastly, project planning and risk management. So how long does the development take? How sure are we that this solution approach will work out? Or do we have to pivot at some point, try out maybe a different AI method? And how long does it take to generate the data? How much data do we need? Because that has a strong impact then on the duration of the data collection, etc. And for project managers that are not AI experts, this can be really challenging because they are asked to respond to these types of questions and have to have then serious discussions with different teams and have to know also which questions to ask. Okay, so now we assume that we have successfully built the system. It runs not only the prototype, but really the deployment version. And now we want to bring this into established use. For the operational challenges, I have divided this into two parts. First of all, we want to bring the system into established use, and then we want to keep it also in the established use. So very important is that the system operators, they have a sense of keeping their agencies. So the operators who work with such a system, they love the performance of the AI, but they fear a loss of control. And the loss of control is not loss of control today, that somehow we take away the knobs and things they can work with, but also the loss of control of making changes to the system itself. Because the systems are not static, they're evolving over time. And sometimes I need a new sensor, or sometimes I have a new chemical mixture I have to work with, and then I need to be enabled to make these changes and not rely in 20 years in the future to have some AI team that comes back and then delays me 2 years before then I can maybe switch the provider of the chemicals that I have as input. And then in addition to that, usability is a concern and visibility of improvements. So you always want to show how much improvements the AI have brought. And once you are in use, you want to stay there. And we are talking about systems that can be in use for 20, 30 years. And that can be interesting, so to say. What you see here on the image, this is Commodore 64 that was in use for over 40 years. So I think it was decommissioned like 2-3 years ago. And in such a long time frame, a lot of things happen. And the systems within which the AI is a part of, these are not stable. And the models have to be adjusted. So there can be slow degradations. So somewhere, I don't know, a pipe is clogging up or something like that. But there can also be structural changes because in a factory, when we come back after 2 years, the factory is looking different. And therefore, the models have to be adjusted as well. And especially for these slow degradations, we want to detect them. So if such a distribution shift happens, we want to know about this. Otherwise, we are working with the wrong assumptions and the performance no longer holds. And then once we have detected a shift, we also want as much as possible to automate adjusting to it. So over this 20, 30 year time period, a question is also, what is the availability of equipment? So if we think about 20 years back, I had a 3D graphics card from 3DFX, German company. Today, this card, it still exists, but I don't have drivers for current Windows. So the question is, can I buy replacement parts? For how long? And am I still even able to run this system 10 years in the future? And then lastly, transmitting technical know-how, of course, as well. So, after this look at the different applications and their dimensions, the look into development challenges and operations challenges, let's also have a look at researchers. So we are coming originally from research and then working with industry, but also in research there are a couple of really long-term questions that we want to have solved. First of all, we want to reduce the sample complexity. We want to use methods that don't need as much data as, for example, a deep artificial neural network. And how can we achieve that? By using prior expert knowledge, making hybrid models that integrate them, by online experiment design, where we not only just take any data, but we select the data point that we want to generate next, because it has a high expected information content, and then overall better ML methods and training methods. We want to have methods that are robust against changes and that can be quickly adapted. So how can we deal with these distribution shifts? And no talk from a scientist is complete without a formula, so we have one. Here you see that the distribution for the data during development is no longer the distribution of the data during operations. And this can happen because of a degradation, a gradual change in the system, but it could also happen because we have worked with simulation data initially. So from that perspective, this sim-to-real transfer from simulated data to the real world is the same as a distribution shift that happens in the actual physical system itself. And we want to detect that and adjust to that. To give you an example of such a distribution shift, let's say autonomous driving. We have a car that is deployed in Iceland, and suddenly the volcano in Iceland becomes active, and we have a lot of ash in the sky, and for that we get black snow. And there was never black snow during the training of these systems, and therefore we have no idea how the car will react. And this is some of the problems then during the safety certification, because you have to show boundaries for the behavior, and these boundaries also have to hold if something unpredictable happens in the environment. So you could have a very tight control about your environment, but in that case it's really, really difficult to have hard boundaries because empirical values for the performance are not enough. And then last but not least, controllability. So how can we describe and ensure the runtime behavior not only in an empirical fashion, but how to say, more clean from a scientific perspective. And this is not solved today, but we really want to have that in order to allow a new generation of AI systems that then actually pass the safety certification that we need when human lives, for example, could be endangered. Explainable AI and fairness, these are helping definitely, but for the domains that I'm working in, the safety certification is the biggest hurdle that we have. Okay, what are we doing today? The Competence Center CC King, Competence Center Karlsruhe for AI Systems Engineering, we create this link between the basic or fundamental AI research and the engineering disciplines. Our goal is to create this new professional discipline of AI systems engineers. We work on the fundamental research, we develop methods and tools that we can then give to engineers to use, and we have a long range of applications together with industrial partners where we're then applying these methods and tools and validating them. But this is only a starting point, so in order to establish AI systems engineering or KI engineering, we collaborate, and therefore we are always looking for partners and multipliers and want to go into a discussion, especially if you are close to the engineering disciplines and are experiencing some of the problems that we've been talking about today. Thank you. I'm not sure if we have much time for questions. I'm giving back to the moderation.
Yes, thank you very much. Unfortunately, we do not have time for questions on stage, but I'm sure you'll stick around, and we have your call to action, so if anyone is interested in an exchange, feel free to do that bilaterally. Thank you very much.